First of all, thank you for the invite. I'm humbled to be on a speaker list of a bunch of professors and doctors when I haven't even received my own yet. But I hope today will be sort of an informative lesson for you all from what I've learned over the past few years, specifically with gallium oxide, but the analysis I'm doing is effectively material independent. I'm going to go through a bunch of topics this presentation, but it roughly breaks into three areas, notably going through the motivations back from the 60s and original derivations for BFOM, and all of the assumptions that go into it, and how we can use those assumptions to sort of draw out the boundaries of what we would expect an ultra-wide bandgap material to behave like, and then moving into more realistic analysis where we can compare to state-of-the-art silicon carbide junctions and compare what do we need to realize that performance in these ultra-wide band junctions, and how can we actually measure it. So by the end, visually, I hope to convince you that you can look at a power converter, take a look at that switching element, and understand why we can derive this Ligas figure of merit in this benchmarking plot, as well as you can look at the 1D approximation for what an electric field should behave ideally as, and how we can turn that into a design principles where, given a certain voltage, you can suss out how thick you should grow an epi layer into what doping so that you get the best benefit. Finally, of course, actually getting into the meat where I'll save you the math today, thankfully, looking at different mechanisms, manipulating the equation such that we can actually see metrics of, for example, what barrier height would you need, or how many traps should you eliminate to be able to actually withstand high field. With that, I'll go to the broad motivation, namely green energy and how we're coming in an increasingly electrified world. As you can see, by 2050, it's projected that we're going to be in the 64,000 terawatt, or for those who use the metric system, petawatt hour. Notably, this amount of energy that we're producing excludes transmission and distribution, which is the cost we pay to just transfer the energy. And if we actually look at how much that costs, even though, as we electrify the grid and we go to greener and greener systems, even though the cost doesn't change, if we're using more and more energy, then the amount of cost to just upkeep the grid itself goes up and up. So we're already at about $500 million per year right now, and it's only going to increase to over $1 trillion per year. Notably, this is just not even considering the losses. There's no perfect system where we have 100% energy going to 100% energy. So if we look at the losses per year, we're doing pretty good, about 4.5%. But if you convert that to dollars, that's several $1 billion, especially with that we're generating electricity. That's just the tax we pay to move it from one space to the other. Now, I'm a very visual person, so I do like to visualize things in different ways. And the way I visualize it is that if we're transferring energy from generation to consumption, that middleman is power electronics. And of course, whenever there's a middleman, they always take their cut. Nonetheless, let's talk about this in more concrete terms. So let's imagine the very basic power converter. I learned this from Professor Afridi. It's like the third lecture if you audit his course, where if we want to lower the voltage, just DC to DC, let's imagine an ideal switch. In the on state, you got zero resistance, no penalty, and the off state, infinite resistance. So you can imagine it just going binary on off. If you switch it at some duty cycle, you get the full voltage and then none. If you add in after it an inductor and capacitor, you can just trust me on this, that you essentially charge and discharge both in terms of voltage and current. There's some ripple to this dVin, but you can effectively flatten out that pulse width. Notably, this isn't just a simple mock-up. If we look at real converters, of course, the switching element is much more complicated, but it has the same generic shape. If we have a switching element that you try to make as ideal as possible at whatever frequency you're working at, and then an output inductor and capacitor. How we realize this is with two different elements. In this case, we're looking at gallium oxide. For reasons I won't get into in this talk, we're limited to unipolar devices, which is also part of why my work's solely been on Schottky junctions and all that. In going from the ideal switch to solid state, we have an N-channel transistor and a Schottky diode. And you can imagine that when we're switching from on and off, we're effectively going between these two states, where you turn on the transistor and you want to let as much current through to charge the inductor and capacitor, but you also want as little leakage current going to the low side as possible. So you want at a certain current, at a certain voltage, very low current. On the other hand, when we are discharging the inductor and capacitor, we want to have as little energy penalty as possible, so you want to have minimum on resistance. And this was captured very well 40 years ago by Professor Baliga in his Baliga's figure of merit, where, of course, if you want the voltage at which you have a certain current to be maximized and the resistance to be minimized, then you just square what you want, invert what you don't, and you can correlate this to intrinsic material properties. And I'm going to take a pause here just to go through a little bit of history, because it's been 40 years and there's sort of been a little bit of a game of telephone, where in some reports they say that instead of it's to the band gap cubed, it's actually to the field cubed, or sometimes we just drop the 4 entirely. So I'm going to go back about 60 years to the original derivation of this, and we're just going to walk through where this actually comes from and what the assumptions are. So back in 1966, Z and Gibbons looked at impact ionization in the conventional materials of the time, germanium, silicon, gallium arsenide, and they noticed this trend where if they normalize it to silicon at 10 to the 16 doping, then it has roughly a 3/2 dependence on the voltage, if you want to predict what voltage will break down at. Knowing that the electric field is related to the square of voltage, then you can see that the critical field is roughly equal to 3/4 of the band gap. If you double the band gap, you get 3/4 benefit in terms of E-crit. 20 years later, or 16 years later, Baliga pointed out that if you have a triangular field profile, then you can just think about the area of a triangle. You get this relation at its critical electric field. You can do some math for the definition of a depletion width, which I've saved for you here to get an expression for what doping you'd have. If you combine these two with the expression for on resistance when you have dominated by drift current, you then get R on specific is equal to 4 VV squared over the dielectric constant mobility E crit cubed. So if we were to be consistent, the BFOM is actually to E crit cubed, but under this original derivation, it's to the EG to the 9/4. But of course, this is still 40 years ago. About 8 years after Professor Baliga, we noticed that this original derivation from Z and Gibbons was a little bit inaccurate. It worked well for the low band gap materials, but as you got up to silicon carbide, it significantly underestimated it. So they went back to the drawing board and they said, let's assume this is a power law relationship. So if you just normalize it to each other, then you get an E crit to EG of roughly 1.8 to 2. 10 years after that, we learned a few more materials. GaN became more prominent. Diamond was coming onto the scene, and they redid the analysis with an empirical fit, and they say, okay, it's not actually 1.8 to 2, it's actually 2 to 2.5. This analysis was again done 20 years later by Professor, I'm going to butcher it, I apologize in advance, Slobodian, where he cut out some of the materials where there's been like one paper or not. And to our best knowledge, this is the trend of E-crit to EG. Now, this is useful for me for power electronics because part of the material motivation is this high E-crit. But this is also true for other fields, for example, like avalanche photodiodes, where you actually care a lot about how this trends like as you alloy it. So knowing that this is the expression for BFOM, you can actually say this is what E-crit should be as a function of bandgap. If you then set E-crit as a constant, mobility as roughly constant, you can generate this plot in the bottom right, which is your traditional BFOM figure where you want to be in the bottom right. You want to block as much voltage with at least on resistance. Notably, as we've gone through the derivation, I've said a few things that we've assumed. One, that the on resistance is given by drift current. Two, that's a triangular field profile. And three, that all three of these terms being the doping, mobility, and E-crit are all independent of doping. As I'll show in a few slides, these are kind of base assumptions that you can modify later. In fact, a paper from 5 years ago actually modified this for some of the wide bandgap materials where your activation energy is quite large. And you can see that actually, if you normalize this ND, which we canceled out, to ND exponential of activation energy, it actually reduces diamond and aluminum nitride above that what you can reach in silicon carbide. This is part of the reason why doping studies in these wide bandgap materials is so important, because otherwise this figure of merit predicts that there's really no benefit whatsoever. As well, is that if we just treat this as a always true analytical formula, let's say you have an unoptimized device and you should be getting 1,000 volts, but you get 200 volts. Well, this formula would then predict that your on resistance should be 25 times lower than it should be. And that's clearly not accurate. It's the same epi, it's just you haven't optimized it. So with that, I hope we're all on the same page, and I've sort of explained where this BFOMs come from and where its shortcomings are. And I'm going to break it down now between the forward bias and the reverse bias. So as we already stated, on resistance is given by the depletion width, QUD. This is basic electronics. But where does it actually come from? Well, I'm going to show some band diagrams and such for my material system, where to date, the best devices are, thick 650 micron substrate, ohmic contact, especially for the wide bandgap materials, is more of a tunnel junction. The drift region, and then there's a Schottky junction. If you're applying a voltage greater than VBI, or in this case, or approximately 5B, we really don't have to worry about the ohmic contact and the Schottky junction. There are some instances where you have a very thin or very conductive drift region where the proportional resistance of the ohmic contact can matter, but in this case, I'm just going to assume that they don't matter. We then get to these two regions where we can also make the assumption that the field will be relatively small. If you're applying 2 volts over 650 microns, electric field is not that high. We can also assume that if the doping is on the order of 10 to the 16 per centimeter cubed or 10 to the 17, you're realistically not injecting more carriers than that. So you can reasonably describe the current by drift current, which is just, J is equal to Q n mu field, V over T, assuming it's a linear field. And you can easily arrange that to get that assumption for the on state. Now, what's interesting, which I find to be more useful than just writing this equation, is understanding what are the predictive limits of it. In that, if we're in one dimensions, current goes straight from anode to cathode. But if we go to 2 dimensions, or we have devices that are significantly small, then we get some additional spreading resistance, which means if we increase the dimensions, we can only increase the resistance. Assuming again that we're in low injection, we're not going to a different mechanism like space charge limited current, for example. So that means whenever I make a device and I measure it, I shouldn't exceed this limit, assuming, of course, not high injection. And if we plot this, we get a plot like this. It's linear in thickness. So I can say, this is the thickness of my substrate. This is the doping of it. You can reasonably say what the resistance should be, the exact minimum. We can then do this for like 2.5 E15 and all the way up to 5 E16. Just see the whole region. I can also do it for substrate thinning, because one of the things we want to see is that substrate actually providing you any benefit, or can we just get it as thin as possible such that we have an ohmic contact and then just have the drift region? And that looks something like this, where you see if you're degenerately doping your substrate to the order of like 5E19, most of the resistance is the drift region anyway. And this will be a theme as I go through some more of the benchmarking figures, where if you're at a highly doped substrate or a lightly doped drift region, substrate thinning really doesn't do much at all. Notably, like I said, this is a minimum, so I can look at some of the devices that I've made in the past. I'll just take one from one-sided PN Schottky PN diode. That was nickel oxide deposit on gallium oxide by our colleague, Dr. Takumi Kanoe from University of Kyoto. And we see that the on resistance that I measure is 5.8 milliohm centimeter squared. And that does indeed follow our prediction that should be greater than or equal to what the material limit is. We can also then look at reverse bias and say, well, where do these assumptions come in? In the non-punch-through case, it's just a triangle. The electric field profile is a triangle, and as I described in the derivation for BFOM, you can assume that in the non-punch-through case, the breakdown voltage is just half E crit times XT, the depletion width. Oftentimes, we don't have a drift region thick enough that it'll be a triangular field profile. It'll actually get cut off a little bit, and this we call punch-through. And this for me, in my case, this is a vertical structure, but this also happens laterally. We're just describing if you have a barrier at one point and you're dropping a voltage across your drift region, what does the profile look like? In this case, gets cut off, and you can also just geometrically describe that the breakdown voltage is the square, which is E crit times XD, divided by that triangle, which is just the depletion width again, multiplied by how much the field is not exactly reduced, but that's slope. So it actually has a D minus D squared dependence, and this will be important later. One thing to note is that since we're cutting off that tip of that triangle, the breakdown voltage for punch through should always be less than non-punch through. Same as we did for the on current for 1D versus 2D, where we said it was an effective minimum. I want to instead look at that for the electric field profile. So this was done in GaN, where they did a deep mesa of 10 microns. And what they saw was it was a very shallow edge termination. They get a lot of crowding of the field near that corner. While if it was very deep, they had a nice one-dimensional profile. If I were to draw this with the x-axis being real space and then the vertical axis being field, it looks something like this. And something to point out, just like how we described previously, that the punch through case is always less than the non-punch through. In this case, if you have an unoptimized device, a 2D profile, we can't increase the voltage anymore because the edge of it's already at E crit. It cannot withstand a field larger than that because it will induce impact ionization and it will fail. So effectively, this entire area is voltage that you cannot apply. But if it's a 1D profile, there's no issue with just raising voltage. So taking it all together, this means that when we go to 2 dimensions, it's now a maximum, not a minimum. So just like before, I'm going to pull up the equations and look at a benchmark plot that I've made. And what you'll notice is that there's a dashed line here, which is where the depletion width is exactly the point where the punch through voltage is equal to the non-punch through voltage. If you're above this line, then effectively the voltage is limited by that truncated case. You can't fully deplete it. And this is what you see for 2E16, and then if I increase it to decrease the doping to 1E16 all the way down to 0.5. And just like the forward bias, I can take the same diode that I measured before. I got a maximum voltage of 1,075 volts. The maximum that I would predict is 4,015 volts. Again, just comparing BFOM, this makes sense. The structure that I have with its doping and the thicknesses of the substrate in the drift region, the maximum figure of merit I can have for that is 15 gigawatts, and I got 0.7. So our predictions thus far are accurate. But the question is, I'm not just trying to validate my own devices. I'm trying to predict what will the field need in the future to increase voltages. And that's where sort of this minimum and maximum can be really useful. So if we return to this plot and I go to, we'll say 10 kilovolts is a nice round number. If we are at 10 to the 16 doping, then you would need 30 microns of material. If you then want instead 20 microns of material, you must reduce the doping to 5 times 10 to the 15, which is still reasonable. But I'm sure I can ask the growers and it's much nicer to only have to grow 20 microns of material than 30. Moving right along, for these plots thus far, I've assumed an Emax of 6 megavolts per centimeter. As you've seen, as I showed in the E crit versus EG plot, there's a few materials, especially on the cutting edge of sciences, where we haven't observed impact ionization yet, or it's not been corroborated by multiple studies. So I'm going to presume that it's 8 plus or minus 2 megavolts per centimeter. And that's also kind of useful because typically you want to operate at the highest field we can before we actually start encroaching on these high field effects. So 6 megavolts is 75% of 8, which is roughly 75% of 10. So you can kind of see this as if the true value is 8, you can operate at 6. If the true value is 10, you can operate at 8. There's a few trends you see. One is that if you're at a certain thickness, if we're stuck at 10 micron drift region thickness, the benefit that you get from decreasing the doping actually becomes less and less as you assume the critical field is higher. So there's actually not much of a benefit at all in terms of the amount of volts you get additional from actually decreasing the doping. And the second is the obvious trend that if you assume a higher critical field, then at the same drift region thickness, you can withstand more volts. Pretty obvious way to read that. Notably, in these two plots that I've shown you before, where I've looked at the maximum and minimum, I've calculated this both as a function of drift region thickness, which means I can just combine them together and have a BFOM as a function of drift region thickness. And this actually tells us where in the design space we want to be. And those plots, again, using 6, 8, and 10 megavolts per centimeter, look something like this. Now, there's a few things I want to point out. Remember how before I said there's sort of a diminishing return for the substrate thinning? If you assume that the substrate is infinitely thin and you're just using the drift region thickness, again, your contact resistance would be worse in that case, but we're not even dealing with current in these assumptions. If you're at 2E16, you have a decent amount of benefit here, like 40-ish% that you're losing from the substrate resistance, which makes sense. The resistance of the drift region is roughly 2E16, 10 micron. The drift region, the substrate is roughly 65 times larger. If you do 2 times 65, roughly 130. So you could say like mid E18. So they have roughly approximate resistances, which makes sense. You're splitting the resistance between the drift region and the substrate. But if you lower the doping, the resistance is dominated by the drift region. So thinning the substrate will give you negligible benefits. Another thing is that the dependence of that in the punch through case actually comes through here. We see that it actually transitions from at low field, it's roughly linear, where you have T squared over T roughly. So that ends up just being T, and it is roughly linear at low thicknesses. As that increases, that T squared term starts to dominate, it starts to turn down. And then at a certain point, you're then limited by this 1 over, it becomes very small in the numerator, and then you effectively get a 1 over T. So you actually have this curvature going down as you increase thickness. And as a visual way to think about this is that there must be a point then where you have the optimal trade-off between drift region thickness and resistance of the drift region, the breakdown voltage that you get benefit from making it thicker versus the resistance you get by making it thicker. It also is a useful thing to notice that this is always in the punch through case. So even if we, in the slides, several slides back where I said, oh, we could do 30 micron, 10 to the 16. Well, that will be much more resistive than if you used a punch in the punch through case. If you want to actually track what this optimal drift region thickness is, it has this form. It's a little messy. I won't make you look at it for much longer, but it has a power log scale where, again, as I'm going to keep reemphasizing just for repetitiveness, if you're at low doping densities where the resistance is really dominated by the drift region, there's effectively no benefit to thinning the substrate. So throughout this talk, I've sort of been looking at voltages and fields and doping and all that. So those of you who've worked with these equations before have sort of noticed that we already have an expression for voltage given a thickness and a doping. So I can relate all of these terms together and actually create this optimal design chart where moving along this line is following the T drift max as we want a specific voltage. So if we're here at 1 kilovolt, then we can read that the optimal thickness we'd want is roughly 3 microns at a doping of roughly 317. And this isn't like a new sort of plot. It's been done previously in the case of GaN and silicon carbide, where they have very similar parameters. This was actually simulated from impact ionization simulations. And because I've noticed that the the maximum beamform's always in the punch-through case, I ended up not even having to do simulations because I know what the field profile should be under the max beamform condition. If I were to overlay these, it looks like this. So you can clearly see it's for the doping, it's shifted upwards, and for the optimal thickness, it's shifted to the right. If we were to sort of look at regimes now, if we're at low, high voltage of about a kilovolt-ish, you can see that the lines here are not too different. You might get a benefit of, you could say like 2 to 8 E16, or you could maybe grow 3 instead of 6 microns. But in established technologies like GaN and silicon carbide, that's not really an issue. So there's not too much of an argument for moving to a material system like GaOx, where you do have the issues of thermal conductivity, the mobility is significantly lower, and as to GaN's benefit, we don't have polarization. So this was already noticed by many other people, but now we're visually seeing from 1D approximations why in the low kilovolt case, gallium oxide is not very competitive, though it may still have its niche uses depending on if you're at like radiation or high temperature. Notably, if we go to high kilovolts, we actually do start to see a benefit. Notably in that as you move down this doping, you start to fight all of the defects that are generating all the intrinsic material nuances. Like for gallium oxide, people have claimed down to 10 to the minus 14, but it's quite difficult. I'm sure I could have Cameron and some of our colleagues in Ohio attest that as you go lower and lower, it becomes much more difficult to get those UID or even intentionally low dopings. So if we're trying to block 100 kilovolts, well, we don't no longer need to be at 10 to the 14. We can be at 10 to the 16, or sorry, 10 to the 15, which is a lot more reasonable. Notably, this is also a technically log plot. That if we're over here on this side, this right here is several hundred microns of drift region. And going down on this, instead of having to grow, we'll say 600 microns, you can grow 100, which when you get to those thicknesses is a lot easier. You don't have to use the full substrate. Or if you do have the full substrate, now you can block 1,000,000 volts instead of 100,000. All this analysis thus far has been current agnostic. I've been relying on E-crit as sort of the maximal value, but I do want to highlight that we don't operate at E-crit typically. And this brings me into the third part of the talk, where I'm going to bring this into more realistic things in the sense of now we're looking at what's the practical maximum field that we can apply. So first, for E-crit, it's defined when the multiplication factor goes to infinity. What that effectively means is if you inject a carrier, it will impact ionize, generate more and more carriers. And when it's infinity, one carrier becomes infinity. So E-crit effectively means if you have any current whatsoever, it gets multiplied to infinity, you get infinite current. Can't realistically reach it because you'll have issues of heating, heat removal, material self-degrades. But for rule of thumb, we can operate at 75% of it just fine, not an issue. For realistic comparison, I'm going to use the 600 volt Wolfspeed diode. They're rated for 50 microamps at 600 volts at room temperature, which if you look at the die size and convert that to a current density, it's about 1 milliamp per centimeter squared. Now, if you have a large area device, this is not much of an issue. But if you have a smaller device like we do in our test setups, where instead of being a centimeter by centimeter, where you get milliamps of current, if you have like 400 by 400, which is still a very large area pad, go at 200 by 200, or maybe a 100 micron diameter or 20 micron diameter, the actual current we're measuring is very low. And that can be an issue, especially if you want to go instead of 600 volts to maybe 10 kilovolts. The resistances you would need at that point is very large, which means the current is likely below nanoamps, which if the noise floor of our system is nanoamps, then it becomes very difficult for us to actually say, am I measuring this correctly? Because it's all hidden beneath the noise floor. And just to put some metrics to it, you can think of it just like we had an on resistance. We also need an off resistance, a specific off resistance, because otherwise we can't maintain that level of current. And the beauty of this having being a specific off resistance is that we can look at the expressions for these current densities, convert it to off resistance, or just plot it normally as current versus voltage. So just like we did for forward bias, I'm going to think, how do we think about specific off resistance? Thankfully, in this case, we can also neglect the substrate and the ohmic contact, and it's really just the junction and the depletion region. And here I'm going to make a clarification where we can think of this as injection mechanisms and conduction mechanisms. Is this device limited by how many carriers you can inject through that reverse bias contact, or is it limited by transport through the depletion region? We know roughly what these mechanisms should be. Thermionic emission, I've lumped together here thermionic field emission and field emission into barrier tunneling. But you also think about non-ideal cases, like if you had trap-assisted tunneling. If you had traps near the surface, where instead of having it going from the metal to the conduction band, you could have metal to trap state to conduction band. All of those are happening in parallel with each other, which means if you have traps near the surface and you have a leaky contact, you may have a phi B of 1, 1.5, or 2, but the presence of traps there means you can't maintain that surface field because the current will just increase. Notably, this is in series with traditional band transport, or you could say trap-limited things like Poole-Frankel current or space charge-limited current. For this analysis, I'm going to argue that Poole-Frankel is greater than or equal to the space charge-limited current, and thus, if they're in parallel with each other, it should dominate as the limiting mechanism. And for the sake of argument, I'm going to treat the band transport in the band as negligible because the amount of carriers we're injecting should be low, even lower than like if we were to see high injection in forward bias case. So what I'm also going to do is explain how I'm going to benchmark this. So if we draw the current versus field, the JE plot, I'm going to fix a current, which is the maximum current I want to exhibit. Okay. So if I don't want to pass more than 100 milliamp per centimeter squared, at phi B of 0.5, that intersects at roughly 0.5 megavolts per centimeter, which means at that current, at that barrier height, that's the maximum field I can withstand. I can increase the barrier height. I can see that the maximum field I can withstand goes up a little bit. Same with 1 EV, and I can do the entire band from realistic of 0.5 to roughly 2 to theoretical 3 EV Schottky barriers. Now, I won't go into the nuance. You can talk to me later about the nuances of actually we're achieving a Schottky barrier that high. In most systems, you just go to PN junctions at that point. If we plot these points here as a function of phi B, we can generate another plot which looks like this, which all this is just reading this value off as a function of phi B. So roughly 0.1, roughly 1.5, roughly 2, just directly across. And this is useful because we can also see that if this point is moved left or right, that corresponds to additional or less resistance. If the max surface field I see is lower, that's not an issue because we've already said that if we have a leaky contact, it'll be on this side. Where this comes into validation is that if it's on this side, we've already determined that this injection mechanism must withstand this amount of current. But if it's to the right, there must be an additional resistance playing its part. In this case, I've said it's invalid, but this is because I'm only considering this to be the dominating mechanism. You could easily say there's a series resistance in there, which explains it. If you also want to think about in terms of specific off resistance, we're effectively looking at going to the right and increasing resistance, where if it's 0, you can't withstand any field at the surface whatsoever. If it's infinity, you can withstand whatever field you want because there's no current. Going to the non-ideal case of trap-assisted tunneling, again, I will save you the math on this. It depends on phi B. and phi t, where as well as the amount of traps you have. And this is the same plot as before, where I'm varying between 0.5, or in this case, 0.67 to 3 eV. And it's not an error that there's only one curve there. It's because if you're limited by trap-assisted tunneling, you're not limited by the injection from the Schottky contact. You're more limited by the emission, by the secondary step going from the trap to the conduction band. So more accurately, instead of varying phi b in this case, because it should always be greater than or equal to the trap state, I'm going to vary instead phi t. Because on this plot, it's not exactly useful to say, oh, look, it's a line. That's pretty useful. But if we instead vary phi t, we can clearly see as you increase phi t, you get less and less current. And this is sort of a heuristic we already know. If you have a lot of shallow traps near the surface, you're going to have a leaky contact. You don't want to have all these traps here to tunnel into that would effectively decrease your barrier. And if you don't take this into account, you'll assume you have a smaller barrier because you're getting more current than you would expect for a larger barrier. In the same rationale, you can see here that there's a slight dependence on NT, but not much. But this is motivating us that not just heuristically, we need to have very few traps near the surface, but mathematically, if we want to, for gallium oxide, fully utilize its crit, we really need to get rid of a significant amount of the shallow traps near the surface. Doing the same analysis for Poole-Frankel current, it's clear it's conducting through the band, and clearly it's not limited by the Schottky contact, because if it were, this wouldn't be the dominating mechanism. We could do the exact same analysis where if we vary phi t, we see that as you have deeper and deeper traps in this region, the transport becomes harder and harder, which makes sense. Again, we can say that if we have shallow traps, then it's not going to provide much resistance at all to the current flow. In this case, I've assumed a uniform bulk electric field. So you could think of this, it would be a rectangular field profile, but you can say this is an overestimation. So the effect is still there, but it'll be minimized because you go from E max at the surface to very low once you hit the substrate. So these are more mathematical reaffirmations of what we already know from growth and heuristics. And I think I'm coming to the end here of everything I wanted to show you today. But I do want to highlight that because you can visualize these in parallel and in series, and that if we do have a trap state of roughly 1 eV below the conduction band, you can keep increasing phi b, but you will reach a point where it's no longer, the current is no longer dominated by phi b. It's more dominated by the trap state. And that's what I've shown here. You could imagine increasing the barrier height, but after a certain point, it loses its dependence. It's dependent on this phi t, which would then be a constant, and then you can't reach a higher surface electric field. Same case for in series, where in this case, it's kind of a benefit, but again, we're overestimating the contribution of Poole-Frankel current, where at low barrier heights, you can inject a lot more current, but then you're limited by conduction through it. Eventually, if you keep increasing phi b, you'll reach a point where instead of being limited by transport, you're limited by how many carriers can you actually put into the drift region, which is then where it picks up its dependence. So hopefully this was a bit digestible. I know it says 102 slides, wasn't really 102, but I hope to have summarized a few things for you. One, in the field of power electronics, these figures of merit have effectively been derived from its direct application in these power converters. And we can easily modify these assumptions for BFOM to motivate the next generation materials, like, for example, the doping efficiency for aluminum nitride and silicon carbide and diamond. Further, knowing a few things about the electric field profile, we can motivate optimal doping, optimal drift region thicknesses, as well as sort of predict how thick of a drift region we would need, to be competitive with, for example, silicon carbide or gallium nitride based devices. And finally, looking more at current and saying, not just heuristically, but actually mathematically, like what is the trap energies and densities that we need to actually be able to fully utilize this material and not just be limited by intrinsic defects. Right. Thank you all for listening.
We have any of time for questions.
John?
Yeah, I had a couple questions. You in that slide where you showed the optimal doping density and thickness plot, somewhere in the 70s. Yeah. So, the work that's been done in your group and by your predecessors, right, uses doping of say 1E16. So are you saying that, and you get, and it's 10 microns thick and, say 2000 volts. So are you saying that if you doubled the doping density, you would get an improved breakdown voltage? Not
particularly. Like I said, this plot assumes several things vis-a-vis that we're at E crit already. And as I was showing through the earlier slides, it's hard to reach the minimum on resistance, and it's relatively hard to reach the maximum breakdown voltage. So if we had a perfectly behaving ideal device, then yes. But in our case, we're not limited by the material itself. We're limited by these intrinsic and extrinsic defects. So if we fix those, then this is, does that answer your question?
Yeah. And then the other question, you made the point about the benefit. You showed silicon and silicon carbide or GaN.
Silicon carbide and GaN, yeah.
Yeah. And your point there was the epi thickness, and it's more of a convenience and cost and engineering perspective that you can get away with a thinner epi with gallium oxide. What about resistance and losses though? So if you multiply the thickness times the doping density times the resistivity, is the resistance going to be the same for each of these cases?
No. Unfortunately, in this assumption, we sort of canceled out doping. As well as we're not exactly worried about the total resistance. We're worried about the resistance comparable to the breakdown voltage. That's what this is plotting. There is a paper from one of the friends of the group, Nolan Hendricks, I believe it was either last year or 2 years ago, where he actually plotted the power losses. It's a very similar concept to what I've done here. I think that would provide more analysis of what you're thinking of, comparing GaN to silicon carbide, different frequencies and power ratings.
I have a couple other I have another question, but somebody else has a question. They can go.
No, you did a good job.
Bennett, thank you for nice presentation. So just a few slides you mentioned that as the electrical field near the edges of the contacts is very important. And this is where the breakdown happens. So is there any, what are the tricks to reduce that electrical field? Just you assume that, so is there any way to spreading that electrical field?
There's many. The easiest way to think about it is, Poisson and Gauss's law. This concentration of field is really concentration of charge. So the simplest way is, a field plate, you just do an MOS structure. Charges, the electric field lines are spread out. The charge is sort of canceled out. That's partly why there's a lot of interest in high K work. But you could also do the same thing with a PN edge termination or insulating edge termination. You just want to move charge away from that edge. You could look up junction termination extension. There's a lot of different terms out there. But mostly it's just moving the concentration of charge away from that edge.
And these technologies, are they specific to the materials? For example, gallium nitride has a kind of high symmetry. So basically the quality of the edges, just when you edge, will be different for different orientation of gallium oxide versus gallium nitride.
It will depend, and this is sort of where the predictive limits become a bit more annoying because, for example, for gallium oxide, there's a bunch of different surface planes. And if you're do a DIT study of different oxides on different surface planes, you get different values, as well as the quality of that interface is going to change. So the principle is the same in all of them. You want to, move charge as well as the electric field lines away from that concentrating at that edge. But each material have its own, specific nuances like nitrogen polar versus metal polar that you have to work around, or like the faceting, like you said, with different surfaces. John again?
Yeah, so it was also related to this. So for field, you show the benefit, right, of this termination, this really deep etch.
I mean, this is also nothing new. Like people have known this concept for.
But my question was really, what is the optimal placement of that? I mean, in your cartoon, you show that it's 10 microns away from the anode. What is the, why 10 microns? Is that the right?
So I'll answer this in two different ways. In this case, they only wanted a 1D profile near the anode. Because the ideal case is you just have a perfect cylinder of material and then there's no spreading whatsoever. Minus, of course, states on the surface. In this case, if you think about the depletion width that they see at their doping, it's less than 10 microns at this specific point. So within the region that's depleted, it's roughly all 1D, which is why it works for them. If you were to, to triple the field you were at, the depletion width would go much higher, and then 10 microns would not be enough. Does that answer your question?
Yeah. Thank you.
Mm-hmm.
Are there any more questions?
I don't think I see any online though, but I might not be seeing it. Yes, I don't see the questions online. Well, oh yeah, of course.
Quick question. So very detailed talk. Thank you for the very detailed talk. Can you go back to the trap energy dependence on current, or current dependence on trap energy? Yeah. So in this region, so once you don't have any traps in the up to 1.5 eV, you get pretty close to the limit of gallium oxide, right? Intrinsic limit of gallium oxide.
Yeah.
Not taking into account surface field at all. But I mean, there's extensive work out of Steve Ringel's group about mapping out the traps, right? Is in high quality material, is there anything in that region?
I think so. I mean, to my knowledge, there was a paper a few years ago where they got like 10 to the 14 doping, which means their traps are much less than that.
Yeah.
But I think this, you can correct me, I believe the state of the arts nowadays is like low E15,
Yeah.
which is still very reasonable.
But they're all like below 1.5 eV, right? So there's nothing in that region. I mean, there's iron, but like if you don't want iron up there.
But then there's the intentional and there's the unintentional defects. Like I, of course, didn't get to it in this talk.
The native defects. I was thinking about gallium vacancies. I thought they were deeper.
It's around, I believe, 0.7 to 0.9, but that's not the donor transition. That's not the acceptor transition. That's I need to pull up the DFT, but it's around, I think,
Yeah,
one.
it's a flat thing, and like it transitions at two things. I mean, I'm thinking where that is.
It's around, to give myself the benefit of the doubt, I think it's 1 plus minus like 0.4.
Okay.
But again, if you
do your epi carefully, like you should have very low values of.
Yeah.
gallium.
So that activation energy is still quite high, even if it's decreasing, is quite high. And Grace and I have had Professor Xing and I have had some detailed conversations about interpreting like the defect kinetics, and that as you're depleting it, you're moving the Fermi level downward. So how does that relate to defect generation? Because now the equilibrium value is increasing because you're depleting it. Of course, you're at low temperature, so it's relative to KBT is not that much, but interesting little DFT nuances of how dynamic is the system, because there is and I'll finish my explanation here. But there was a recent paper where they actually looked at electromigration of like nickel. So at these high fields, you do see like just defect generation natively, just because of such high fields, like moving impurities. Like in that paper was nickel just throughout the lattice, seeding gamma gallium oxide, which then leads to failure. So in that case, even in a perfect material, you get this defect generation, which then lowers the Emax you can actually reach.
The refractory layer in between.
Yeah, I mean, I think there's plenty of studies like the thin, I forget which high K dielectric it was. Might be was it zirconium oxide, I
I
think?
was thinking more like, your thin ruthenium or iridium oxide.
Yeah, or something like that. I think those would also be well, though you'd have to work with oxide noble metals.
Thank you.
Yeah, did you have a question?
Yeah, can you maybe back up and paint like a bigger picture? What sort of motivated you to delve this deeply into this realm?
Mostly, like you said, the motivation was to get a realistic picture of what's possible. Especially because in the research space, we tend to deal with milliamp per centimeter squared, but the eventual goal in these converters is to switch amps of current. So how close are our test structures to what we should actually observe when we scale this up? And then the issue comes because if we're trying to get to high fields at low currents or high voltages and low currents, that implies a high resistance, which then, as the name of this talk implied, beneath the noise floor, we lose information about what's going on. So all of this was me attempting to illustrate what is actually happening, putting some metrics to it. Even if we can't measure it in these small test devices, it should obey these laws still.
That actually was my question as well. That is, those are beautiful plots. However, I think a vast majority of us in the audience will not be able to grasp the insights that those graphs are conveying. Yes? So that's the reason Joe asked this question. Let's just use this chart as an example. There are plenty of folks here who are growing. What is the implication for the growers? And there are also plenty of people who are making devices. Then what are the implications they should take away from this chart, right? So for this chart, I know that you went through also relatively quickly, so that we can have this conversation. Let's use this chart as example. It is plotting current density versus surface field. What does it mean as far as a grower is concerned? Or the earlier question Professor Hari asked about a trap. Which slide was it? Can you go back to that slide one more time? Not the 6. Also, if Arjan is here, Arjan will be characterizing trap states and energy states as well as the density of those trap states. Yes. What information can you give to the growers from this one?
I think the best way to think about it is that electrically, this corroborates what the growers already know, and you want a very high surface quality.
Wait. First of all, in this chart, which corner is desired corner? I mean, will you actually have a plot? The very first thing is which corner represented where I want to be.
So
Yes.
ideally in the JE on the left, you want to be in the bottom right.
Yeah, can you point it out?
Ideally, you want to be down here, but that effectively implies extremely high resistance. But of course, in this case, this line demarcates what's governed by this tunneling mechanism. But ideally, you want to have as little current as possible. If you go back to if I go back.
It's okay. Now you can point out the ideal curve you want everybody to take away from this plot is this dark red line on the rightmost, correct? You
Effectively.
want them to follow this line, yes?
That or lower.
Take a look at one more time. Do you want a phi t to be 0.1 or 2?
Of course.
That's what I'm saying. You have a lot of different curves here. You want everybody to remember the desired mode of operation is the dark red on the rightmost, which means you wanted to introduce deep trap states, not a shallow trap states. Okay, correct? So that's what I think the audience is asking.
Yep. 2 questions. Professor Vlad or Dr. Vlad and I guess Dr. John.
Just question. Because since we like in the engineering school, we want to improve the balance of the energy, just using that like electrical tricks, materials. During your research, did you kind of find any information how we can reduce the consumption of the energy by improving the social behavior. That's, for example, to see if everybody start unplugging this power supplies overnight, just keeping the light off overnight, and just like improving just if an ideal like individual, how much we can improve with that.
So I believe you're basically talking about like sort of my base research into this sort of concept of how much energy is using.
We are talking
I'll-
about fractional percent.
It's probably very small, but I'll also say that every little bit counts. Because as you can see here, one of the interesting things, if you compare the 2024 report to the 2023 report, data centers actually wasn't on there. This is actually a new occurrence that they're like, okay, well, 8% of the energy is going to be in data centers in 25 years. Well, these predictions change, up and down, but there's a little bit we can do, but generally that's sort of like a society-wide thing. Like if we're all utilizing AI and all this and implementing it into research, like how much can we do? Not too much. That's on the electrical engineers at the data centers to figure out what's the minimum energy per, computation for the architecture.
Last question, John?
Yeah, the last question. You said several times, right, that thinning the substrates doesn't matter. And I just would like you to expound on that. I mean, it's got a poor thermal conductivity and, you will produce heat. And as it heats up, you'll take a hit in your mobility and therefore your resistance is going to increase. And so, yeah, so I mean, thinning the substrate will help is a part of addressing the thermal, which does play a big role in transport.
I would argue it's an issue, but I'm not sure how big of an issue it is in the sense of this is for an athermal analysis, of course. Like I've assumed mobility is the maximum, from 200 down to like 70 as a function of doping. If you increase the temperature, it'll go down, but by how much? Like if it goes down by a factor of 2, you've increased the resistance by a factor of 2, Is that a big deal? Kind of, but it's not a huge change. In this case, what this plot's illustrating is in terms of the total resistance of the device, the substrate is like 5 or 10%. If you want to get 5 or 10% less resistance, then yeah, you can thin the substrate, but how? But that's sort of, I'm highlighting the trade-off there. Of course, with heat, you can do like microchannels and all that, which is slightly different. The math will be different. Right. Well, it's 1 p.m. Thank you all for coming. I do appreciate the opportunity to speak with you, especially with, like I mentioned, I'm still humbled by the amount of professors and doctorates and just the many decades of work and that I got the opportunity to talk to you all today. So thank you. Enjoy the rest of your Friday. I'll see you.